Hi, my name is Manish Gupta, and in this video, I will talk about Retentive Network, which has been nicely claimed as a successor to Transformer for large language models. So let's try and understand this new architecture of retentive networks. Let's get started. What is RetNet or Retentive Networks? As I mentioned earlier, it's a foundational architecture for large language models, which helps to simultaneously achieve three things: training parallelism, low cost inference, and good performance. Now that's basically what one desires when they want to basically make use of large language models for industry style settings. So it basically helps you get strong performance, low cost inference, and training parallelism. Now, of course, the standard transform models essentially help you get training parallelism and strong performance, good performance across several tasks, but inference is not low cost. Inference takes quite some time, right? Recurrent neural networks, RNNs, LSTMs, and so on can get you strong performance and low cost inference as well, but then training parallelism is not there. Essentially, it has to be done sequentially, right? Then there are these linear transformers, a variant of transformer networks, which help you get training parallelism and low cost inference, but then at the cost of performance losses. Right? But what RetNet tries to get you is basically a combination of all the three: low cost inference, training parallelism, and strong performance. So in this video, I'll try to get into details of how this is done. This video is going to be a little mathematical in nature. However, I'll also provide enough intuitions to make it easy to consume. Okay. So retention mechanism sort of supports these three things, which is what allows you to get these three things, right? So there are these three things called as parallel representation, recurrent representation, and chunkwise recurrent representation. Parallel representation, as we will see in detail in this video, it allows you training parallelism. Recurrent representation enables low cost O of one inference, right? And then chunkwise recurrent representation helps you deal with very long sequences, very long input sequences with linear complexity. Okay. Now, as a result, what has been shown in this paper? Well, people have shown that the inference cost of RetNet is length invariant. Now, what can be better than this, right? When using transformers, people are always worried about the large length input sequences. Hey, if you give them, then because quadratic complexity of transformers, that just doesn't work. However, RetNet helps you deal with it by coming up with a model that is length invariant. RetNet is consistently competitive in both scaling curves as well as in context learning. So in fact, if you look at this chart for a 7 billion 8K sequence length, 7 billion model with a 8K sequence length, RetNet decodes 8.4x faster compared to a standard transformer. So if you look at throughput, right, it is 8.4x faster compared to a standard transformer model, right? So the green one is RetNet and the gray one is standard transformer. If you look at the RAM required at inference time, well, the RAM required is 3.4x smaller, so or rather 70% smaller compared to a standard transformer. Similarly, if you look at latency, well, it is 15.6x smaller latency compared to a standard transformer, right? So huge improvements or huge gains, right? Overall. Now, so as I said during training, so this is for inference, right? So the training part is not shown here, but we'll look at it in detail later. However, in short, RetNet achieves 25 to 50% memory saving and about 7 times acceleration compared to standard transformer. So 7 times faster you can train your model and 25 to 50% memory savings. Great. Okay. Now, how does it perform? So this is a language modeling task where the perplexity is being shown. So perplexity lower is better. And what you see is that beyond around 2 billion sized models, RetNet takes over transformers. So RetNet gives you lower perplexity. Lower means better. So therefore, RetNet basically performance on language modeling is better compared to transformers, especially when it comes to 2 billion plus models, 2 billion parameter plus models. Okay, so what is the broad architecture of RetNet? RetNet consists of stacked L identical blocks. This is one block, right? Similar such blocks, L such blocks essentially are there in RetNet architecture, right? And the standard models, basically, these folks trained 3 different models with different number of such blocks. I'll talk about those configurations later, but in general, you can have L such blocks. Now, each block actually contains 2 sublayers, an MSR sublayer and a feed-forward sublayer. So compared to standard architecture of transformers, where this is self-attention sublayer, They have MSR sublayer. MSR stands for multi-scale retention. And of course, we'll look at it in detail as to what this layer does. And then there is a feed-forward sublayer, which is basically exactly the same as in standard transformer models. Okay. Like standard transformers, they also have residual connections and they have pre-layer norm, right? So Vaswani transformer did not have pre-layer norm, but then several variants of transformers proposed later had layer norm being applied before these other sublayers. So it has residual connections, also pre-layer norm. Okay. So let's basically consider the input as x, so which is essentially n tokens, n equal to the length of x. So basically n different tokens are going in as input. RetNet encodes X autoregressively. So it's basically more or less the decoder architecture. So it basically the left side attends onto the right tokens. So therefore it is autoregressive encoding. Okay. Now let's take the input X and encode it using embedding metrics into these tokens. So capital X. So if this was the first layer, X0 will get passed in here, X1 will be there, X2 will be there, and so on, right? So L layer, at the end of the L layer, you will basically get XL. Okay. At any layer L, well, it basically takes XL minus 1 as input, and then it applies this RetNet block, this entire block of 2 layers, you can call it as a RetNet block, and gives you the output. So what is RetNet block? Well, RetNet block basically contains 2 sublayers. Essentially, the first sublayer takes X and then applies layer normalization on top of it, and then an MSR sublayer on top of it. And then there is a residual connection, combination of the two, residual connection, right? So then the feed-forward sublayer basically takes this Y, applies layer norm, and then feed-forward sublayer on top of it, and then applies a residual connection. And that's basically the output to the next RetNet layer, output to the next RetNet layer. Okay. So LN is basically, of course, layer norm. And then the feed-forward sublayer is very simple. It basically is just taking the input, multiplying by a weight matrix, and then applying GELU, the activation function, and then apply the other weight matrix. Okay. So far, so good. It's basically pretty simple at this stage, right? It's basically just a standard architecture, just like transformer decoder, except that rather than the multi-head self-attention layer, you have MSR sublayer. We'll understand what this MSR sublayer does. OK, so RetNet basically is a recurrent network. So transformers removed the recurrent connections, but then RetNet has brought in the recurrence back again. Recurrence essentially helps in lower test time performance, lower test time latency, right? So how is this recurrence encoded into the sublayer is what we'll understand here. Okay. So the idea behind this slide is to be able to take recurrence and be able to express it in a parallel form such that you can have training time parallelism. And at the same time, at inference time, you can actually still refer to it as recurrence and therefore have inference time low latency as well. Okay. So again, here there's some math, but then I'll walk you through the math. Right. The idea is that you take X, right? You take X, so your inputs are basically multiple words, and XN is a particular word. So essentially, or tokens. You can basically consider them as tokens in general, but maybe I'll use words interchangeably. Okay, but you have tokens, and then for every token, you're going to represent every token as XN. So there are n different tokens. Okay. Now, the first step is to actually project it to Vn. So you take a token and then you multiply by some weight matrix so as to think of it, or a weight vector, and you get Vn. Okay. It's best to think of Vn as a number for this slide, but then later we will see it can be sort of generalized to a vector, as we will see in the matrix form in the next slide. Okay. But think of it for now as a number. So you have Xn, which is basically an embedding for a token, and then you multiply it with some VW, which is a weight vector. And let's say you take cosine similarity, and then Vn is that similarity number. Okay. So in some ways, what is Vn? Vn is a single number representation of your word xn, right? So then you have multiple words coming in. So essentially, you process the previous word and then you have the next word. So what you want to do is to basically just use the typical recurrent formulation. So essentially, if you remember the recurrent formulation, you have if you have this one as Sn minus 1, and this is Sn. So you essentially think of this guy as Vn and this guy as Vn minus 1. And you can think of this weight matrix as Kn transpose, and then you can think of this weight matrix as A. So that is how Sn is computed using the standard recurrent formulation. So Sn equal to A times Sn minus 1 plus Kn transpose Vn. Okay. So now here A is a D cross D matrix. So essentially, if these layers are D in size, if these layers are D in size, and you think of Vn as a single number, so then Kn is just a 1 cross D vector. Okay, so Kn is a 1 cross D vector, A is a D cross D matrix. Now, after this Sn is computed at any time point, you would want to come up with a representation from this Sn. So let's call this representation as On. And the way this On is computed is by multiplying Sn by Qn. So you have Qn here, and then you have Sn. So you essentially, that's how you get On. Now you might be thinking as to how do you get this part though? So Qn is right there, and then there is Sn. So the idea is that Sn is basically this entire thing. However, what you want to do is to sort of unroll this and then replace Sn minus 1 with its unrolled form, right? So essentially, if I were to write this, I would write it as follows: Qn times Sn. I'll try to replace Sn, right? So I'll write it as A times Sn minus 1. I'll not write Sn minus 1, but because I want to, unroll it further. But, this is how I'll write it, right? Now, Sn minus 1, if I were to unroll further, I would basically write it as A times Sn minus 2 plus Kn transpose Vn, right? Or rather, n minus 1 and n minus 1 there. Okay. So now if you look at it, right, if you keep doing this process several times, you will essentially end up with a 0 here. And remember, in a recurrent neural network, the first hidden layer is essentially initialized with zeros, which basically means over entire unrolling that you would do, this entire term would basically just get down to 0, right? Get down to 0. What you would be left with is essentially these terms, for example, this term and then this term multiplied by A, and then K transpose n minus 2V and minus 2 multiplied by A square and so on. Which is how, and these additions basically come up as sum here. So which is how you have basically gotten this formulation. So it's essentially the same Qn guy just brought inside. And then you have m equal to 1 to n. And then, for the first n equal to 1, you have for the first word, or the first token in the sequence, you'll be basically considering A raised to n minus 1 because, it has been multiplied n minus 1 times by this matrix A. Right? And then you have the same, you have the K M transpose and Bm, which is basically coming from these terms, Okay. So that's that. Now, so that's basically how we have, in short, written out, written out the formulation of On. So what is On? On is basically the embedding of this particular token that you would want to pass to the feed forward layer. Okay. Now to concretize it, right? I mean, now if you think about it, right? Qn, Kn, A, all of these are weights to be learned in some ways, right? So in fact, even V for that matter, right? So essentially, how did you really get a V from X? So all of these have to be learned. So let's basically make them data dependent. So essentially, the way you compute Q is basically by doing X into WQ, like you do in a standard transformer. Similarly, the K is X into WK, like you do in a standard transformer. And then, rather than calling Q and K as weight matrices, you're basically calling WQ and WK as learnable weight matrices. Okay. The next thing to deal with is about this guy A, right? So what is A? Now, to make the number of parameters smaller and also to be able to encode positional embeddings nicely. So remember, A actually is going to take care of recurrence. Unlike transformers where there is no recurrence and therefore you have to have positional encoding separately, here what you could do is to sort of wrap the positional information into this A nicely, right? So let's see how this gets done actually, right? So rather than having too many parameters A, what you want to do is to essentially diagonalize A. So what is diagonalization? Diagonalization of a matrix basically means finding out 3 factors of the matrix, beta, P, and beta inverse, such that when you multiply them, you basically get A back. And this matrix P is a diagonal matrix. All of its elements, non-diagonal elements are 0. Only the diagonal elements are non-zero. When you do this kind of stuff, what you end up with is a beta and beta inverse, and then a P, which is basically a diagonal matrix. So what is beta? So when you're doing this thing, right? By the way, what is going on is the following. you're taking the matrix A and changing its base, and therefore, this beta matrix is also called as change of basis matrix. So it sort of takes your A and so while changing the basis, what beta does is that it rotates A, and therefore the columns are aligned with the eigenvectors of A. So basically, these columns in beta or beta inverse are aligned with the eigenvectors of A, and this matrix P basically, which is a diagonal matrix. So let me just show you how the matrix P looks like. So you can consider everything else is zeros, only the diagonal elements are non-zero, and you can represent this element as gamma 1 raised to ei theta 1, gamma 2 ei theta 2, up to gamma. So let's say if the matrix A was D cross D matrix, right? So therefore, this is going to be gamma D ei theta D. Now, you might be confused about why is this thing, or what is this thing? So recall from your school days that e raised to I something basically means complex numbers. And when you're dealing with matrices, diagonalization can actually lead to complex numbers, right? So therefore, what you have is gamma, which is essentially the eigenvalues of A, and theta, which is essentially the angle that each eigenvector of A is rotated by, right? So that is that. So that's the diagonalization process. And again, why are we doing this? We're basically doing this so as to avoid the large number of parameters in A in some ways. And also, finally, this also helps you reach a parallel implementation of this entire process, which is important for training time parallelism, faster training, right? Okay. So what you have done is to essentially diagonalize, and this is conceptual in some ways, right? Don't literally diagonalize it. So essentially what you've done is to express A in terms of beta beta inverse. And for general form, essentially you call P as gamma e raised to I theta, where you will have a gamma going from 1 to D and theta going from theta 1 to theta D. Okay. Now the beauty about this is that you can therefore represent A as beta times gamma I e raised to theta beta inverse. And if you have to basically now remember, we have to have A raised to n minus m. A raised to n minus m can then be written as beta inverse, but then gamma e raised to minus theta can be written as n minus m, raised to n minus m. Yeah. Now further, what you could do is remember this Qn is actually XWQ and K, and the nth row from it in that senses, and then there's this XWK and the nth row from it in that senses, right? So there's WQ and there's WK here anyway. Now what you could do is to take this beta and take this beta inverse, absorb beta into WQ and absorb beta inverse into WK. So what that leads you with is essentially, essentially what you end up with is that this becomes this. Okay, so your sum remains the same, Qn remains the same, and then Vm remains the same, and even K transpose M remains the same. But then this guy essentially, it becomes gamma e raised to I theta. Where does beta go? Well, beta has been absorbed into this and beta inverse into this. Okay. Now that's that, because they're just weights to be learned, right? So essentially, you can always combine two weight matrices, multiply them, and then say, hey, it's a single weight matrix anyway. Okay. Now that's that. Now what you could next do is to actually divide this into two parts and have this part separate and this part separate. Okay. Further, what you could do is to take these gammas outside and have gamma written out like that. And then you have this K part and this Q part and this K part, right? VM remains the same. Notice that this transpose has been converted to this guy because this is basically the complex conjugate operator. So remember, since we are dealing with complex numbers, we have to essentially care for a complex conjugate transpose, right? This is complex conjugate transpose operator, which is essentially taking the transpose of the matrix, but at the same time, also absorbing this minus sign inside. Okay, so that's that. Now, why is this entire thing required, right? So why did we do all of this? We did all of this because we didn't want to suffer from the high training time latency because of the sequential behavior here. This is sequential in nature. Okay. Now what we have done here, it is sequential because Sn depends on Sn minus 1. So you have to compute one by one. However, by doing this in this form, where each of these parts, each of these things inside the summation can be computed in parallel, what you have obtained is training time parallelism. So you could basically compute all of these terms, all of these n terms in parallel, and therefore not suffer from training time latency at all. So I've copied that stuff here. And now I'm going to generalize it. Remember, we were thinking about a perspective of a single token. Now we will basically think about the entire sequence. Okay. So if I basically, so now therefore we will see two different forms of what is going on in the network or in the retention layer, right? So remember, retention layer does not need to have position encodings as such explicitly because, well, it has recurrence in it anyway. So for this retention layer, there are two forms in which we have worked with it, right? So one form is essentially this parallel form, and the other form is essentially the recurrent form. Okay, recurrent form is easy. So we were essentially, we were essentially in the recurrent form doing this, right? So we are saying Sn equal to A times Sn minus 1 plus K times K transpose Vn. The same thing is written here, but in matrix form now. So Sn is equal to gamma times Sn minus 1 plus Kn times Vn. Okay. And then you would say retention is going to be, you take this Sn and multiply by Qn, and that's basically your output of the retention layer. And that's basically essentially, the recurrent form of doing it. And that's great. In fact, this form is actually very nice at inference time. At inference time, you can essentially compute all the way up to Sn minus 1. And then when you're trying to generate the next token, well, all you have to do is to really compute these and just add them. And then, of course, rank by probability and get the overall, sample from the probability distribution, final probability distribution that you obtain. Okay. So in short, this is how the recurrent form looks like. You take the input, you essentially get a query key and value kind of representations. You take the key and the value matrix, multiply them, and essentially, and then, you take the previous recurrent state, you multiply that by gamma. Gamma is more like a decay factor now to think about it. Okay, but we did mathematically look at what gamma is. It's the eigenvalues of the matrix A. Remember? So that's that. And once you've gotten Sn, so that's basic, that serves as the recurrent state for the next token. And essentially, once you have gotten this Sn, you can also multiply it with Qn and then do some normalization. Specifically, in this case, they do group normalization, which I'll talk about on the next slide. And that gives you the output distribution. From this output distribution, you can sample and get the next token. Yeah, that's the recurrent formulation. But then at train time, what happens is the parallel formulation, where the idea is to really implement this guy in matrix form. The way it is done is you take the X, you essentially get a Q, and you take the X, get K, and you take the X and get V. Right? But in this case, QKV are a little different from what you observe in standard transformers. V is the similar one, but Q and K are different. They have this Hadamard product or the element-wise product being done with another thing called theta, so as to incorporate for this e raised to in theta, right? So so this theta guy is basically in theta, and this hat guy is basically just its complex conjugate. So a complex conjugate transpose. So which is basically this guy, right? This guy or other transpose. So therefore, it's sort of this guy, the complex conjugate operator. Okay. Now remember, there is this gamma guy also that needs to be taken care of, and which is why you essentially say that my retention overall is going to be defined as the QK transpose, which is here, multiplied by the gamma guy. So multiplied by the gamma guy, which is essentially represented as D. So remember, it is an autoregressive formulation. So if n is less than m, then this D guy is 0. You mask it out, right? But if n is greater than equal to m, you basically consider it to supply information for this token. And that is what you capture in D. Okay. Now that's that. So that's basically the parallel formulation, which is actually used at train time, Okay. So the parallel formulation is as follows: you take X and you get QKV, and you effectively obtain QK transpose Hadamard product with D into V, and that helps you get your O. Right. So remember here, you don't do it per token. So essentially, you take the entire matrix Q X and then you process it in parallel for all the tokens, right? However, in the recurrent formulation, you actually process it in one token at a time, one token in the input sequence at a time. Okay. So now this matrix D is very fancy, right? So essentially, this matrix D is combining causal masking. Remember here, there's causal masking, right? So essentially, you use the left tokens to supply information for the right tokens, while also doing exponential decay. So this gamma guy can also be thought as exponential decay along the relative distance, as you go from left to right. Okay, now can you combine the two? So we saw the same retention thing being expressed in a parallel form and in a recurrent form, right? So that's the nice part, that they have been able to sort of express the recurrence in terms of a parallel formulation. Now, for long sequences, so there is a trade-off, by the way, between parallelism and recurrence, right? So the trade-off is in terms of latency and the RAM which is required. So now, can you exploit this trade-off by a hybrid? Can you exploit, or can you express this trade-off in a hybrid form for long sequences? So when the sequences are too long, at train time, you don't want to basically do parallelism across all the tokens, right? Because that then will require a lot of RAM. So what you could do is to take very long sequence and split it into chunks. And then the idea is that within the chunk, you basically do parallelism, while across chunks, you do recurrence. Okay, that's the beauty. And that is what is called as chunkwise recurrent representation. Chunkwise recurrent representation of retention layer. So the idea is you basically do a hybrid of parallel representation and recurrent representation. And the way you do this is to basically take your long input sequence. And remember, this is useful when you have very long input sequences. You chunk them out, you divide them into chunks, each of length b, right? And within each chunk, you're going to use parallel representation. Across chunks, you're going to use recurrent representation. Okay, this is not new formula. This is just the same old thing. I just copied from the previous slide. So here, this is the parallel formulation that we saw on the previous slide. This is the recurrent formulation on the previous slide. Now you have a large input sequence X. You have divided into chunks, and each chunk is of size B. Now, if you want to compute the retention output of the ith chunk, the way it is done is basically what is shown here. Okay, so this notation square bracket I represents the ith chunk. Okay. So now remember, within the ith chunk, you're going to do parallel computation, which is basically this one, right? And across chunks, you're going to combine their representation in a recurrence kind of a way. Okay, so therefore, if I were to compute the RetNet representation Ri, right, of the ith chunk, what I would do is essentially to consume the information of the previous chunks. I mean, in a recurrence way, the way I would compute is essentially use Ri minus 1 coming from here, so Ri minus 1, here R and S are, analogous, right? So, and then I essentially have K and V, which is basically coming from here, K and V. And since essentially I'm combining, representation from B different tokens within the Ri minus 1 chunk, I'm going to also have gamma B. Okay, so that's basically that. So that's basically just a recurrence kind of a formulation. However, I must also incorporate the parallel computations within the chunk. Okay, so therefore, to do parallel computations within the chunk, I'll take the Q matrix part of within the chunk. So remember, B is the size of the chunk and I is the ith chunk. So Bi to Bi plus 1 is essentially the rows corresponding to this chunk, the query matrix corresponding to this chunk. Similarly, for K and similarly for V, right? So QKV, I have the rows corresponding for this chunk. I can actually use them using this formulation. Using this formulation, I can use them here so as to compute inner chunk within chunk representation for all of those tokens. Okay. And then here what I've done is so this part 1 is basically inner chunk or parallel computation. Part 2 is essentially cross chunk or computation from all previous chunks. Okay, so remember to care for all previous chunks. What I have basically done here is used recurrence, right? So essentially, if I use Ri, I'm already capturing Ri minus 1, Ri minus 2, and so on. So all previous chunks are being cared for, right? However, the query should come from this chunk, and therefore I have Qi here, right? And then, these gammas are adjusted just for the current chunk. But then I have to remember decay all the gammas of all previous chunks which Ri minus 1 contains. And therefore, I must multiply it with this psi, which basically cares for multiplying all previous chunks by gamma I plus 1. Okay. So that is that. Now that essentially, in short, on this slide, what did we talk about? We talked about a hybrid scheme of parallel and recurrent formulations or representations of the retention mechanism. Okay, so now the last, conceptual stuff is about gated multi-scale retention. Okay. So whatever we have been doing so far is anyway multi-scale retention. And what I'm going to do in this slide is to combine those stories all together and sort of give you an overall perspective of how this retention MSR layer works, right? So remember, MSR is called multi-scale retention, and the way it works is what is explained on this slide. Input is X, right? And what we looked at so far was one retention head. Now we are not going to call it attention head. It's more like retention head now. Okay. So we use H retention heads, okay, in each layer, where D is the head dimension. D is the dimension of the head. So if D is the head dimension, then WQ, WK, WV are our learnable parameters of size D cross D. Okay. So the MSR layer essentially assigns different gamma for each head. So remember, we have different heads. For each of those heads, we'll be diagonalizing the A matrix, and therefore we'll have gamma e raised to I theta. So therefore, for every head, there is a gamma and there is a theta, right? So that's basically for different heads. So these gammas are specifically assigned per head, and they are shared across layers. Okay, they are not learnable. Neither gamma nor theta are learnable. The only learnable weight matrices are WQ, WK, WV, and later we will see there are other weight matrices which are learnable, but gamma and theta are not learnable. Right? So gamma is actually assigned, and it is assigned in a way such that it is different for every head in the layer, but actually it is shared across layers. Okay. So in fact, gamma is assigned like that. So 1 minus e raised to lin space. Lin space just means that you at equal space starting from log 1 by 32 to the head. So if this is the first head, second head, third head, and so on. So h can be 1 up to h, right? So you choose numbers that are equally spaced by log 1 over 512. Okay. So that's that. So essentially, you take those different values of gamma, and they form they form gamma 1, gamma 2, your diagonal matrix essentially. And so that's basically gamma. Okay. So the way you do this is you essentially compute the retention values per head. So for the ith head, you're basically going to use gamma I value from this guy, right? So gamma I value from this guy. Okay. And then you're essentially going to essentially compute these head representations for each of those heads. Let's say if you had h heads, you'll essentially combine all of them, concatenate like you would do in standard transformer. Okay. And then in standard transform, after concatenating, you would do a layer norm, but here they do group norm. Basically, they do normalization per head because heads have different gamma scales, and that basically leads to different variances per head, and therefore they do normalization per head separately. Okay. Uh, After you're done with that, you essentially take your x. So here, what is going on is essentially, you take your you have computed your y, and you take your x, you multiply it with WG, a new learnable weight matrix, right? And you apply this kind of a gating mechanism called swish. It's a nonlinearity activation function in some ways. And then you do element-wise multiplication with y, which is essentially what you've computed using the retention mechanism. Finally, you multiply with another learnable weight matrix W output, and that's your MSR. Right? So much of this also happens in standard transformers, except that group norm does not exist. There's layer norm, swish is not done. You just multiply directly and so on. And W0 exists in standard transformers as well. Okay. Now, interestingly, because of group norm, you don't need to do this standard normalization, which happens in the standard transformer part. You just take QK transpose and so on, but you don't do this normalization by square root of D. That is not required. Okay, so that's about the retention transformer, retention, network architecture. Okay. Now, how does this compare with respect to the architecture of recurrent neural networks when you compare across several different parameters at train time as well as inference time? So let me talk about that. At train time, essentially you use parallel or chunkwise recurrent representations. You use chunkwise recurrent representations for longer sequences. If the sequences are not long, let's say 500 size sequences, you can actually just use parallel representations. Chunkwise recurrence is especially useful for long sequences, which is efficient both in terms of floating point operations and in terms of memory consumption. Right? At inference time, you always use the recurrent representation for autoregressive decoding because it helps you reduce the memory and inference latency. So you can always cache the current state, and that helps you determine the next state very easily, with very low inference latency and also very low memory requirements. Okay. Now, in comparison with attention in standard transformers, retention actually removes the softmax also, right? And therefore enables recurrent formulation, which significantly makes inference faster as well as less intensive on memory. Yeah. In this paper, the authors actually trained three different sizes of retention networks. 1.3 billion, 2.7 billion, and 6.7 billion with 24 layers and 32 layers respectively. Hidden layer sizes as follows: 2048, 2560, and so on. Notice that the FFN size is just twice of the hidden layer size compared to standard transformers where it is 4 times, right? 8 heads, 10 heads, 16 heads in the 3 different sizes. Okay. Now, conceptually, if you compare standard transformers, the RetNet essentially has training level parallelism, which is also there in standard transformers because of the attention mechanism, but it is absent in recurrent neural networks. Right? Recurrent neural networks are sequential, so you can't train them in parallel. Yeah. However, in recurrent neural networks, you have inference cost, which is constant because you can cache the previous state, and all you need to do is to always take the current token and just output. Do some computations and output stuff. Right now, in transformers, that becomes ON because it would depend on all previous tokens. Right. In transformers, also from a long sequence perspective, the computations are quadratic in nature, but in recurrent neural networks and RetNet, they are basically linear in nature. Performance-wise, transformers and RetNet give you really good performance, as we will see across different tasks. Accuracy, performance here means accuracy across different tasks. However, recurrent neural networks have been shown to not perform that well. Okay? So as you see here, for as we talked earlier as well, for language modeling perspective, the perplexity of RetNet is way lower compared to the perplexity of the transformer, especially when you care for larger model sizes. Here are more results. Essentially, they compared the performance of transformers versus RetNet across a whole bunch of tasks. And on all of these tasks, what they found, whether you do 0-shot or 4-shot inference, you basically find that RetNet performs much better on average compared to the transformer-based models. What you also observe is that if you compare transformer or even transformer with flash attention with RetNet across different model sizes, you find that the memory consumption drops, right? So standard transformer, for example, takes 61.4 GB memory for 13 billion model, while RetNet takes like around 46 GB. Throughput. So if you look at throughput, essentially in words per second, words outputted per second, you observe that the throughput for RetNet models is much larger than the standard transformer model. This is training time. This is training time. And then what happens at inference time? At inference time, this is what happens. So at inference time, if you vary the sequence length essentially, and you look at the memory consumption, you observe that the transform memory consumption increases with the increase in sequence length. However, RetNet memory consumption is pretty much constant. So therefore, sequence length now is not really a big problem with RetNet models. If you look at throughput, well, RetNet's throughput is way larger compared to transformers throughput, especially when the sequence length increases. Transformers throughput continues to decrease versus RetNet's throughput actually stays constant. Okay. What is also interesting is that what happens is as you increase the batch size. So as you increase the batch size, the latency for standard transformer models with different sequence lengths increases. But for RetNet, essentially, it stays more or less the same, even with 8,000 as the input sequence length. Okay. So that's that. That's about retentive networks or RetNets. In summary, in this video, I talked about retentive networks for sequence modeling. It enables various representations, parallel, recurrent, and a hybrid one called as chunkwise recurrent. RetNet achieves significantly better inference efficiency in terms of memory, speed, and latency, thereby providing you training parallelism, competitive performance, low latency, as well as very good performance at inference time. Right? Overall, RetNet or retentive networks does look like a very reasonable successor to transformers for large language models. However, like everything, time will tell how much people start using RetNet compared to just using standard transformers. Of course, if this becomes popular, then very soon you will see more papers coming in where retentive networks are used for multimodal representations. Just like standard transformers started getting used for multimodal representations and for many other similar tasks. Okay, so that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.